Hi all, this is Kyle from Better Explained. I just want to give you a quick intuition on how to learn trigonometry intuitively. Normally when you study trig, you'll see diagrams like this, and you might have a mnemonic like SOHCAHTOA, so sine is opposite over hypotenuse, and cosine is adjacent to hypotenuse, and tangent is opposite over adjacent. The problem is it's not really learning. You're memorizing an acronym and you have some letters flying around, but you're not really visualizing anything. And it's really hard to get an intuitive understanding from this kind of diagram and this kind of description. Half of our brains are dedicated to vision, so why don't we use more kind of visual analogies to help understand things? So that's what I'm going to do today. Just as background, I basically see trigonometry as anatomy. So if you imagine an alien coming to Earth and trying to study people, until he starts giving names to the different parts of the body, it's really hard to find the connections. But if you name the different parts like head, arms, legs, torso, you can start kind of seeing relationships. So one common one is that for most people, their arm span is equal to their height. So that means that if you find somebody's jacket, you can spread it out, estimate the hands, and now you have a pretty good estimation of their height as well. So the cool thing is, once you've started labeling the pieces, you find these connections, and then if you know one fact, you can sort of work your way around to the other ones. The really cool thing, though, is that when we're studying math things, we're actually the aliens, and we're studying these weird creatures in the math world. So basically, things like triangles and circles, those are the creatures running around the math world. If we have better labels for the parts of these shapes, we can find connections that we missed the first time. So that's kind of the goal of trigonometry, is to sort of learn the anatomy of math, and because of that, we'll get all these connections for free, right? So just like in a person, their arm span is equal to their height. In triangles, there's certain connections, in circles, there's certain connections, and the more that we know about them, we can sort of use those facts to kind of get free results that we wouldn't have before. So let's just take a look. The key analogy that I like to use is I like to imagine a dome, a wall, and a ceiling. So let's start with the dome. If you have a triangle, you can sort of imagine it being part of this larger dome. So imagine you're in the center of a dome. You have this kind of arc going around you, and let's say you just want to hang up like a movie screen. Now, depending on where you point to hang it up, you'll have actually two facts about it. You'll have the height of the movie screen at that height, and also the distance to it. So if I point up here, the movie screen would have a certain height, and there'd be a certain distance away. And the height, we just call it the sine, just like another name of the body part. We have a sine, and then the cosine is the distance. One thing I like to do is imagine a sign, like a street sign that's hanging. So the sine is vertical, and the cosine is horizontal. And just with that, we sort of have two labels. So I can point anywhere, and if I hang a screen, I have a height of the screen, and I have a distance. And even from here, we can make some kind of intuitive analogies. If you want the biggest screen possible, what do? Well, you point straight up, because you're hanging it from the very top of the ceiling, and it'll be a huge screen. It'll be right on top of you, but it'll be a big screen. Or if you want the tiniest screen possible, you point straight ahead. And when you point straight ahead, it's actually right at the floor. There's no screen, but it is far away. So that's sort of the visual insight I think of when I imagine sine and cosine. Now, one little thing that nobody ever told me is that everything is in terms of percentages. It doesn't make sense to give an absolute height, like 15 feet in the air. It doesn't really mean anything. You don't know how high that is on the dome. But if you say, oh, 15 feet is actually 95% of the height, well, now you know you're really near the top. So with trigonometry, instead of using absolute numbers, we all use percentages. And an easy way to kind of work with this is just always imagine you're on the unit circle. So if the radius or the radius is 1, if the hypotenuse is always 1 when you're going around, that means that the division to get the percentage is just divide by 1. You don't have to do anything. So the height is the sign. You don't have to make a division. For any kind of arbitrary triangle, you do need to do the division. So that's why you have the opposite divided by hypotenuse to get a percentage. But in your head, I prefer to always think of the unit circle, and I don't have to do the division. So that's one thing that nobody ever told me. All these functions are in terms of percentages. So things like sine and cosine, the max percent they can ever be is 100%, right? You can't, if you're in a dome, the max height you can have is 100%. The max distance you can have is 100%. You can go negative. If you put it underground, that's negative 100%. Or if you put it backwards, that's negative 100% that way. But still, the range is from negative 100 to positive 100. There's other functions that can go beyond 100%, like we'll see right now. So imagine that instead of the dome, you actually have a wall right next to it. So let's say you have a neighbor, you're trying to watch things inside your dome. He builds a wall right next to you, and it goes infinitely high. what do? Well, maybe you want to hang the screen on the wall behind instead of on your dome. So you point to an angle, and instead of hanging on the dome, you go up and hang it on the wall. And so the idea here is that, okay, now we have some new words, right? Because we're not going to the dome anymore, we're going to the wall. I consider the tangent is actually the height on the wall. The distance to the wall is always 1. It's always that unit distance. And then we also have kind of the ladder distance to the top of the screen. So the ladder distance is this red guy here. We call that the secant. And the height actually on the wall is called the tangent. And there's a few mnemonics. One I imagine is this kind of naked guy here that we have. We're going to project him on the wall. And so then I ask, oh, the tangent, the tangentleman is on the wall right here. And then as you're climbing the ladder, you're wondering, oh, can I see him? Can't I? You can see him, can't you? So secant is sort of what you get when you climb the ladder. Again, use your own analogies, but that's just the one I get. You get the naked dude over here, tangent, and then you get the secant over here. So with that, we have 2 new words. So if we're talking about the dome, we have sine and cosine. If we're talking about the wall, we have tangent and secant. And then the next step actually is the ceiling. So imagine, your neighbor's not too happy about having, naked people projected on his wall, so he builds kind of a ceiling all the way above your dome. Okay, well, now we need to talk about how to get to the ceiling. Let's say you want to build a ramp and to go talk to your neighbor. You pick an angle, and that's the angle you're going to build your ramp at. So the height to the ceiling is 1, right? It's always that unit distance. The distance that your ramp would travel is called the cotangent. And the kind of, again, the diagonal, the hypotenuse, the distance up to the ceiling is called the cosecant. And these mirror, so that the cotangent and the cosecant are sort of the mirrors of the tangent and the secant. And I keep it straight by thinking ceiling and co, so they both start with C. So, the cotangent, okay, that's the distance on the ceiling, or the kind of the width of the ramp here. And the cosecant, the secant used to be the ladder distance. Well, now it's kind of the ramp distance all the way up to the ceiling. So this red guy here is the cosecant, and the cotangent is this distance of the ramp here. Now, we have these connections. Can we put them all together? And we can. I like this version better than the SOHCAHTOA because we can sort of see everything together, and we don't have ratios. We have actual quantities to look at. So we have our dome. Within the dome, we have sine and cosine, and again, the hypotenuse here is 1. So sine is the height, cosine is the width to the screen. For our wall, we just go out a little bit. We kind of stretch things out. So 1 is the distance to the wall. Sine kind of goes to tangent, right? So it gets a little bit higher, and tangent is just the name of the height on the wall. And then secant is the kind of hypotenuse. It's just the ladder distance to the top of the screen. And the last step is just going to the ceiling. So if we build a ramp up to the ceiling, now we have the ceiling here. We kind of have the height, it needs to stretch out to 1. Cosecant is that kind of hypotenuse that goes to the ceiling. And then cotangent is sort of the width of the ramp. So all these things are connected. If you look, you see that sine and tangent are kind of the same thing. One's just a little bit larger. Cosine and cotangent are sort of similar. And secant and cosecant are kind of similar too. It's just, they're all connected. They're all just the same triangle getting bigger. And that's exactly what it is. Trig is just about noticing these connections. And when we do that, we get these cool things like this. From the Pythagorean theorem, we can, find relationships about right triangles. So we know that cosine squared plus sine squared equals 1, or sine squared plus cosine squared equals 1 squared. Go to the bigger triangle, tan squared plus 1 squared equals secant squared. And go to the biggest triangle, 1 squared plus cotangent squared is cosecant squared. So these kind of facts, I don't memorize them. I just look at this triangle, or the set of triangles and realize they have to be true. So I don't memorize it. I just look and say, oh, okay, well, tan squared plus 1 squared is secant squared. Yeah, because the triangle makes it happen. The next other cool thing is that we have these ratios from being similar triangles. So if we have similar shapes, the internal ratios for the shapes are the same. So for example, sine to cosine is the same as tan to 1, which is the same as 1 over cotan. So sine to cosine equals tan to 1 equals 1 over cosine. We're just comparing the height and the width. And again, it's the same triangle, just zoomed in or out, so the height to width ratio is the same for all of them. And we can do it for other parts too. We can say sine to 1, which is sort of the height to hypotenuse. Well, that's the same as tan to secant, which is the same as 1 to cosecant. So we get all these kind of relationships for free, or for not much work, and you don't have to memorize things. Normally people just cram all these facts together, but just draw this diagram out and you'll see that, these are the connections. It's right there. Now, one thing is, don't get stuck in this particular diagram. If we change the angles a little bit, now we hit the ceiling first instead of the wall first, and so the order switches a little bit. These connections are still the same, right? The connections are the same, it's just the order that they happen in might be different depending on what angle you pick. So don't lock yourself in and think that secant is always bigger than cosecant. No, that just depends on if you hit the wall or the ceiling first. But the connections, right? The secant to tan, cosecant to 1, 1 to sine, that will always be the same, even if the order switches. Okay, so that's sort of my quick aha moment. There's some examples in the actual post, so if you look in the description, you'll be able to click on it and go through it. But in summary, just remember these diagrams and just think of trig as anatomy. It's a way to kind of label the parts of these little weird math objects, and those math objects appear all over the place. In the real world, we say we have the head of an organization, mob bosses have muscle, spy groups have eyes and ears. Well, the idea of a triangle shows up in a lot of math objects. And so if we can describe a triangle really well with all these little pieces, then we'll have better descriptions of other math objects as well. With that, happy math.